All right. Part two of the GLASroom Planetarium show. Here we go. Time for the observing session. It's going to be a ton of fun. So first things first, I'm assuming everybody who's here was in the earlier show. So quick introductions. I am Adam McCulloch, the planetarium specialist here at Glass Education, and my co-host is our professional astronomer and all-around amazing person, Katya Gosman, who is going to be teaching us all sorts of awesome things about the Stonehenge Observatory, while we look for a bunch of different cool things in the night sky tonight. So Katya, do you want to, should we check where the sun is? Oh, you already did. Oh, 1 second, Katya. I'm sorry. I had the wrong output. You're gonna have to start over, Katya.
Did no
They
one
couldn't
hear
hear
me?
you. No.
Okay. That's okay. Can people hear me now?
Yes, you're good to go
Yes?
now.
Okay. So, I'm sorry everyone missed that. I was not aware that no one could hear me. So anyway, to reiterate again, for those of us joining us for the first time, welcome. Right now, we are going to be observing using a telescope that is called Stonehenge Observatory. It is located in Sonoma, California, in a vineyard, which is great. It's privately owned by someone that really loves doing education outreach and STEAM outreach. And so they have very generously let us have some time to go do our educational endeavors here with the scope tonight and lots of other nights as well. And so, as you can see, the screen that you see might look kind of familiar. It's actually Slack. A lot of you now have probably used Slack. It's very popular for teams and schools and stuff. And so this is actually a special channel on Slack called Itzamna. It was named after Mayan god of the sun, I think.
Yes.
Mayan god, yes. And so some people wrote a program, like a command line type interface, so that we can send commands that the telescope in California can read, understand, and use it to move. And it's really cool because I can just like lay in bed, take my phone, and go control a telescope in California. How cool is that? And so this telescope is a 20-inch reflecting Ritchie-Christian design. So it uses mirrors, and we can do a lot of things in it. And one of the coolest things is that it actually has a nice CCD camera attached to the telescope with 6 different filters. So we can go take images and actually make color images. And we'll show you a couple of those later on during the night. And so First things first, using Itzamna, before we open up, we have to check where the sun is. So these are, as you can tell, the commands that you can ask Itzamna to do. And the one to check the altitude of the sun is \sun, very simple. And we want the the sun, we want the sun to be at least below -15 degrees below the horizon. And that's because when the sun has just set, it's not fully dark yet, as you might notice. Like, you go out and like Google tells you the time of sunset, but you might notice that at the time of sunset, you can still see things. Like the sky isn't fully dark. And so we're waiting towards, so it can be fully more dark so that we get towards something called astronomical twilight. And so we gotta wait a few more, probably like 10-ish or so minutes until the sun goes down a bit. And then we can open up. Well, we can actually probably open it up right now, but we can't take any pictures until then.
I think we're
And
good.
so,
I think we're good too. If you want to open the dome, and we
yeah.
can start talking about some of the objects we plan to be viewing tonight.
Sounds good. So to open the dome, we do the command, very interestingly named, crack. Oh wait, first I have to lock the telescope. First things first. First we have to lock it, which means that I, as the user, now have control of the telescope, and I'm the only one that can send it commands, which is useful so that other people don't try to take control of my observations. But I'm also going to share the lock so that Adam and other students after O can use the telescope as well. And now I am going to crack open the telescope. So crack open the dome, and this will take a little bit. And so, Adam, how about you tell us a little about what we're going to be observing tonight?
So one of the first objects we're going to be looking at is actually the first object that was imaged by the Great Refractor. Or at least we're going to make sure of that. It's up there. I'm pretty confident that it is. It is a globular cluster by the name of M5. And so, Katya, would you like to show us how we can test something if we're not sure with Itzamna?
Yes. So, yeah, first thing you want to do is you always want to make sure that your object is in an observable location. So what we do, is we do the command \find and then the name. So in this case, I would just type in M5. You can find other objects as well in different catalogs, or you can just type in coordinates, like a right ascension and declination. And so it looks like Itzamna has found a celestial match. That is good.
So if you're also joining us after our show earlier today, we did not have time to fully explain what objects that start with an M are from, and it's because they are part of the Messier Catalog. So, Katya, I know it's one of your favorite stories. So while we wait for this one to be in the right position, why don't you tell us what the Messier Catalog is exactly?
All right. So, Messier Catalog is named after a French man named Charles Messier, who lived in the 1700s, i.e., the 18th century. Messier was a comet hunter, and so he was interested in just that, comets. Wasn't interested in really anything else at that point. But back then, telescopes weren't the most powerful tools that you can imagine, at least not like now. And so a lot of things kind of look the same. They look like little fuzzy blobs in the sky. And so Messier decided to make a handy-dandy list for him and astronomers like him of things to ignore when looking for comets. This list included things like nebulae, clusters of different kinds, galaxies, supernova remnant, a couple of other random miscellaneous things. And ironically, even though he meant this as a list of things not to look at, it has actually become a list of some of the most well-known, easy to find, easy to look at, fantastic to look at and image objects. And so a lot of the things that we tend to look at, just stargazing or at star parties, are from the Messier Catalog. And so in this case, our object M5, um, as you can see, all I do on Itzamna is I go to do \plot, and it will make a nice handy dandy chart for me of the altitude versus the time. So on the x-axis on the bottom, we have hours where the origin is set to right now and time going forward as you move to the right. And then on the y-axis, we have the altitude in degrees. So how high above the horizon is this object? For Stonehenge, we have a limitation that we cannot view any objects that are below 30 degrees. And so in this case, our object is indeed above. It is around 38-ish degrees. Looking from this, so it is good to go for when the sun has set below its horizon, which we're close, -14. Got one
So
more
close.
degree down to go.
Okay, so then I'm going to talk a little bit about the object before we go and look at it. So if you guys were in the earlier portion of our show, you heard about what a globular cluster is, and we did zoom in on it, but we want to take a live image of this globular cluster to kind of just take a look at it. And it's kind of cool to think that 120 years ago, almost to this day, so about 6 days from now, it'll be 120 years since this image was first captured by the Great Refractor. And can you remind me, what is the scientist's name? What's Ritchie's first name? Do you remember, Katya? Anyway, it's not important. He was the first one to take an exposure with the Great Refractor using the plate camera, and it was actually a 5-hour exposure. But we're actually going to be able to collect a similar amount in only seconds. Just kind of a good example of the advancements in technology, and especially because we're using a telescope that's half the size.
Also, it's George Ritchie.
George Ritchie, thank you.
George.
Good old George.
Yeah.
And so he was the first one to take an exposure using the Great Refractor, and there were many after that. One of the things we talked about during the previous show was how many globular clusters were actually how many exposures were taken of globular clusters between Ritchie and Barnard that were then later analyzed to look for that proper motion in them and to really analyze them, done by Dr. Cudworth, who then used the 40, 50 to 70 years after a lot of these images were taken. So how are we doing on
the sun?
Yeah.
I think it'll be a little while. Yeah, we gotta wait like a couple more minutes. We're so close here. Yeah, the problem with the telescope being in California is that it's also 2 hours. We're 2 hours ahead of it. And so that's why we have to hold this part of the show this late at night when a lot of you probably all want to go to bed. And as we get further on into the summer, it'll probably be even later.
The optimistic way to look at it is after June, the observing sessions will get earlier and earlier.
That's true.
But yeah, so for now, we want to talk a little bit about one of the other objects that we'll be going to, and it'd actually be helpful right now to introduce one of the very famous scientists. And if you have been paying attention to the Yerkes stories that we were doing a couple of weeks ago, one of the winners was mentioned a story about one of his interactions with Morgan. And Morgan was a very prolific scientist at Yerkes Observatory. And one of the biggest things that he is known for is his discovery of the Milky Way's spiral arms. And so, one of the things that we want to look at are some of the galaxies that inspired him to think about what our galaxy looked like and to investigate that. So, a lot of the imaging that was done, a lot of the exploration that was done from Yerkes was into specific stars, looking at kind of the structure around our galaxy and looking at kind of double stars, binary systems, and exploring kind of the life cycle of said stars. All right, and I see we are still just a little bit away from actually being able to take our first image. So once we are able to, Katya, what is the next step that we have to take?
Right. So once we are able to take an image, that means I can execute the command \pinpoint. And so there's two kinds of pointing we can do. We can do either \point or \pinpoint. For most objects, we do \pinpoint. The only ones we don't do that for are bright objects, such as planets or bright stars. The reason being is that the command pinpoint will go to the area where it thinks the object is, and then it'll actually take a 10-second exposure of whatever area of the sky that it is currently looking at, and it'll send that 10-second exposure image to a service called astrometry.net. And this is a program that you can use. Anyone can use it. It's free. You can just find it online. And what it does is it analyzes any image of the sky that it's given and can determine the exact coordinates of the center of that image and what you're looking at. So you can literally go out, take a picture of the sky with your phone, assuming that there's enough stars in the image, it'll identify what you're looking at. One of our friends, she was on the show last time, said that she took a picture of a galaxy that she didn't know what it was, sent it to astrometry.net, and it told her the galaxy. So it's a pretty cool, useful tool. And so the reason that it does that is so that it can center the object exactly in the frame of view. So you don't get like your galaxy off on one side or something. And the reason we don't do it for bright objects is because taking a 10-second exposure of a really bright thing will ruin the image from the CCD for some time afterwards. So you'll kind of get like a ghost of the object in all of your frames continually for the next couple of images that you take. So come on, sun. Let's see if we can do that yet. Yay! -15. Okay.
There we go.
We got this.
All right.
So now we can pinpoint.
And so now we are going to go and actually take an image of the same object that Christian Ritchie did 120 years ago. And another thing that you
George Ritchie?
George Ritchie, sorry. I was thinking Ritchie Christian, like the telescope
yes,
design.
The pair.
So I had half of it right. So now, once you can tell that it does take a little bit of time to actually point at the objects, and as Katya mentioned, it has to then take a small exposure, send it in, make sure it's lined up. So one thing that you learn very quickly when doing astronomy is that patience is a very valuable thing. And whether you're a patient person or not, if you love astronomy, you end up becoming patient, or you find other good ways to distract yourself during. But one of the things, I know, Katya, we did talk a little bit about kind of what globular clusters are in the show, but would you like to go over that one more time while we wait?
Yeah. So basically what we're going to be looking at is huge conglomerations of like hundreds of thousands, sometimes even millions of stars. They're all very old stars, so like 12 to 13 billion years old. And for reference, most astronomers but found out that the universe, they posit, is around 13.7 billion years old. So pretty close to the actual age of the universe there. Um, and so these are old, very old, mostly red stars that are all bound together under their mutual gravitational attraction in this nice clump. And actually, fun fact, we call them globular clusters, but in other places like Australia, they would look at you funny and tell you that you're saying it wrong because others pronounce it as a globular cluster, which indeed that is correct. It's not, if you look at an image, it's not actually just like a flat circle. It is indeed a three-dimensional sphere of stars that just looks flat to the eye. And that is, oh,
Look at that. Your
pinpointed.
timing is
Yay!
impeccable.
Wonderful. And so now once a telescope pinpoints, what we usually do is we like to take a short 10-second exposure just to make sure that the image is in view and everything is good with the tracking, etc. And so image 10 to clear. Where clear is the filter that is being used. StoneEdge has 6 different types of filters. It has 3 broadband filters, the GRI standing for green, red, and infrared, that, as the name suggests, are centered at wavelengths that let in green light, red light, and more infrared light. And then there are 3 narrowband filters, the sulfur 2, oxygen 3, and H or hydrogen alpha filters that are narrower, much narrower than the wideband filters, as the name suggests, and lets you see those elements in whatever object you're seeing. So H alpha, you can see regions of H alpha in your image, and if they don't exist, then there just won't be anything that pops up in that filter. And so these are really good actually to find out if those kind of elements exist, and they can tell you about things like star formation, for example.
All right, and Katya, now we have our image up. I've got it zoomed in, and
Wonderful.
wow, does it look beautiful.
Yeah. I love them 5.
So this is not only a great object to image, but it's also a wonderful object to actually view through a telescope. And I was actually able to talk to Dr. Cudworth this week, and he let me know that this is in fact his favorite globular cluster. So an extra added little bonus to this one. When somebody who studies them for that many years tells you that this is their favorite, good chance it's one of the best ones.
Yeah.
And it's one that was observed from Yerkes for many, many years, and all of those plates have been used endlessly since. And so, Katya, do we want to take a couple broadband images? Do we want to head on over to our next object?
What is our next object? M51?
Yes.
All right. Yeah, let's go to M51.
All right, let's head over to M51.
We can make a cool image.
So something we talked about earlier was Morgan, who, as we mentioned, was kind of the person who discovered the breakthrough that our galaxy is a spiral galaxy, and was able to actually kind of show where those arms are. One of the reasons that he thought to look and wonder what our galaxy looks like is because when we look out at night, and you look up into the night sky and you find kind of the big arm of the Milky Way, it just looks like a cloud that goes over the night sky. And unfortunately, right now where we are with where the sky is positioned, the Milky Way is low on both horizons. But especially during the summer, the arm of the Milky Way will straight across the sky as it passes through the summer triangle. And if you get a chance to go somewhere where it's dark enough to see it, you can't actually make it out here near Yerkes. It's a little tricky, and you kind of have to know where you're looking, but you can still find it. But normally when we look at these other galaxies, we're able to look at their structure and classify them. But when we're looking into our galaxy, all of that stuff kind of gets in the way and we can't really get a view. Kind of like trying to take a picture of your house from inside. While you can get a great view of the interior, you're never going to get a really nice exterior view. So we have to kind of look at everything inside our galaxy and try to map it out to get an idea for what we think it actually looks like. And he was the one, by taking measurements of different stars, able to put together that we are in one of the spiral arms of a grand spiral galaxy. And one of the absolute best examples of a grand spiral galaxy in the night sky is M51, and is cited as one of the galaxies that inspired him, along with M101, which is the Pinwheel Galaxy in Ursa Major, and we may also go there tonight as well. And here we are. Now we're going to get
You have such good timing too.
We're just on a roll today.
Yeah.
And now a couple more seconds of time filler until our beautiful image pops up. And oh, wow, is it clear tonight?
Oh, that is gorgeous.
Wow.
And so, as you can tell from this image, is indeed is a spiral galaxy, but really I should more concrete, it is actually two galaxies, two spiral galaxies that are merging with each other. There's one up top, and you can see the little one, little companion down there. And so, contrary to what you might think in common sense, is if two things collide, they go smash right into each other. Galaxies don't necessarily go boom, right, and smash. What they do is kind of little dance. So they kind of like, they start apart and then they'll become like gravitationally attracted, and they kind of like spin and dance and disform themselves into very irregular shapes sometimes until they merge in one. And so this is an example of it's in the process of merging currently. And there are some really cool examples out there of galaxies. There's one called the Mice, because I guess they look like mice to whoever named them. Those are also two irregularly merging spiral galaxies.
Yeah, a cool thing to think about is if you go out and look at the Andromeda Galaxy, it's the largest galaxy in our night sky, and on a good night is visible to the naked eye. Unfortunately, not during this time of year. It's already too low in the sky, but in the winter and spring, going out and looking for Andromeda is a must-do. And that Andromeda Galaxy is actually on a collision course with our Milky Way. Now, the Andromeda is bigger, but the size difference is not quite as stark as the Whirlpool and its companion is. But our two galaxies will actually merge in about 2 billion years. So now, what do you think, Katya? We can either go to the Cat's Eye Nebula, or we can go take a look at another grand spiral in looking at M101.
This is gonna take a G-band image.
Oh yeah, let's get our color, our images.
Yeah, we can make a color image.
Katya, did you want to tell everybody a little bit about what do you mean by make a color image?
Yeah, right. So, if you remember, I told you before that Stonehenge has 6 different filters that you can use to get in different wavelengths of light. And so what we can do then is, I mean, you can do this in various methods. I use a program called DS9, which is a very typical program that most, if not all, like observational astronomers, astrophysicists use to look and analyze image data of observational data. And so, 1 second. What we can do, one of the things is you can take 3 of their filters and assign them to red, green, and blue specifically, and play around with the scaling and stuff until you get a color image. And so you take all of them and stack them on top of each other, and that will create a color image. Because right now the images that you're seeing are just black and white. And that's also why whenever you see an image, like a beautiful image from like Hubble or something, right? Those are all false color images, as in you can pick and choose what filters to add to what color channel. It's all up to you. You're kind of like the artist in this situation. Um, Things don't actually look like that if you're looking at it just like out in space, usually.
I love the. I want to look at the other filters.
Yeah.
So here you can start to notice slight changes as you look through different filters. Different things start to poke out. And you can also then see why a lot of these images need to be reduced. So we take the flats and we're able to then subtract a lot of this noise, kind of specifically this hourglass shape that you're seeing. But once that's gone, you're able to get these amazing color combined images. And Katya, I believe
Yes.
we will have a color image to show them very soon.
Yes. Uh,
So again, as Katya mentioned earlier, the colored images really are kind of a false colored images. You're just kind of taking different light and representing them in an image. One of the things that we should make clear is that not all galaxies are spiral galaxies. It just so happens M51 and the object we're going to go to next, M101, are both grand spirals, as they were the inspiration to look for those spiral arms, and it just happened to be that our Milky Way is also a grand spiral. But sometimes the galaxies look like nothing more than just a big elliptical blob. And those happen to be called elliptical galaxies. And those are typically larger, older galaxies that don't have these big swirling arms where new stars are actually being born. Because these arms are typically look like this because there's a lot of star forming going on in them. So there's all these things that you look for. So there's big clouds where the gas is kind of condensing down, where new stars are being born. We call those nebulas. There are a bunch of really great ones. Unfortunately, right now at this time of the night and time of the year, there aren't a lot of good ones to image. So we'll be looking at a different type of nebula in a little bit. But so we have all of our images. Katya, do you want to get us a colored image, please?
yes, I can post it while the telescope is pinpointing. Oh, it might not show it up until after the telescope pinpoints, but I can 51. Oh, I guess it did go.
There we go. Let me
Yeah.
zoom in on that and tell us a little bit about how you did this.
Yeah, so this is an example of a color image. And I went on DS9, and on DS9 it's relatively simple to create an RGB image, as in all the steps you do is just you make a frame, an RGB frame, you upload the image that you want to use for your red filter. So I use the R band. You upload the image you want for the green filter, etc. And then you can play around with different scalings and stuff to get different features to pop up and all that. And after playing around with that, that is an image I created. So you can very clearly here see the dust lanes and different star forming regions.
I really like how this brings out a lot of the kind of the stuff that you can see in the actual spiral arms.
Mm-hmm.
And you can start to see more of the arm that goes up and out over on the top. Sometimes with galaxies like this, if you do even longer exposures than the ones that we did, you can really start to pick out a lot of things that you would not have noticed, especially if you were observing them optically through a telescope eyepiece. Oh, and here we go.
And yeah, I can also show you that if you stick your images a different way, you can get a different coloration. For example, if this would... Oh, haha. No wonder.
What's going on?
Do a thing. I want... Did this save in the wrong folder? It doesn't.
Well, and just as a reminder, if you guys have any questions while we're going through, please put them into the chat room. I would be happy to kind of talk about them live.
So this is a different coloration that you can do just by playing around with filters and settings.
So one of the things...
Don't mind the name, I named it wrong.
Oh.
I know it says NUC4565, but I named it incorrectly there.
Gotcha. Well, we'll just ignore that.
It's in the wrong folder. Yeah.
So yeah, so when you see those big, beautiful colored images, a lot of them are usually just CCD images that were stacked in that way, then taken into Photoshop and really spruced up a bit. So the other object we have here that we just recently took, and oh, Katya, would you like to move us to another object, or would you like to take a couple of images of M101?
I'll take a couple of images. This one is interesting.
Okay. Yeah, even if you just took one or two longer exposures to really pull out the arms. So as you can see, there is quite a bright core to M101, and you can start to see the spiral arms as they go out. There's a decent amount of noise in this image though, but you can still find these spiral arms. And the pinwheel, well, obviously not the most creatively named, there are actually multiple pinwheel galaxies, so sometimes you have to actually clarify which pinwheel you're talking about. You can definitely understand why it was given that nickname with how much these arms tend to wrap around. So let's see, what's the next exposure you're taking? A 60-second?
Yeah, 60-second red. Yeah. Where are we moving after this?
So we are going to be going to the Eye Nebula. And do you need the C dignifier, or do you want the NGC?
I think it's 6543.
Very easy to remember. Yes, you are correct.
Yes. Oh, this one looks... the R-band didn't turn out as well, but that also, it has artifacts of noise and stuff coming from the CCD and the sky and stuff.
Yeah, unfortunately the filter did mess with this a little bit. So normally we would actually wait to really start to analyze these images after they were reduced and cleaned up a little bit. When you're observing live, you can't be too picky though, so we just kind of have to take a look at what the preview shows us and go with that. But now we are going to go take a look at a completely different type of object from the things that we're looking at. So far what we've looked at are things where, well, the first thing we looked at is one of the oldest things in our universe. Globular clusters, as Katya mentioned, are very, very old. Almost all of them older than our own galaxy. Then we looked at other galaxies. Most of these ones that we've looked at are younger galaxies, as they still have big, large star-forming regions, just like our Milky Way galaxy does. Now we're going to be looking significantly closer to home, but at a completely different type of object. So the things that we've looked at so far are mostly made up of stars and gas and dust. Now we're going to be looking at something that is the remnants of a singular star. So what we're going to be looking at is called a planetary nebula, and it's kind of what's left after a smaller star ends its life. Katya, would you like to talk a little bit about kind of the process that a star goes through when it turns into a planetary nebula?
Sure. So actually, our sun is going to become one of these things in like a couple million billion years. Don't worry, don't worry. You're safe for now. Um, so basically, when you have a star that is less than 8 solar masses, like our sun, so it's less than 8 times the mass of our sun, it's not big enough to go supernova at the end of its lifetime. So instead, here's what happens. So our sun currently is on what's called the main sequence. So it's the path where a star spends most of its lifetime. Sun is very happily right now burning hydrogen into helium every single day. Hydrogen, hydrogen, helium, fusing that together. At some point, the sun, though, is going to run out of hydrogen to fuse, and so it's going to start fusing heavier and heavier elements. It'll start fusing helium, and then it'll start fusing carbon, whatever other elements it goes through continually. And as it fuses heavier and heavier elements, it doesn't fuse all of them. Like it reaches a stopping point at some point, but basically, while it's doing that, is it will start expanding into a red giant phase, what it's called. At that point, our sun is assumed that it will either come very close to or actually go and swallow Earth. So at that point, we probably don't want to be on this planet. But don't worry about that again. That will not happen in any of your lifetimes. And so when it does that, it's going to start expanding and shedding outer layers of ionized gas. And those layers of ionized gas are actually what form the nebula that you see. And what's left on the inside is the remnant of the star called the white dwarf. And it's basically ionizing the gas around it, or exciting all of the photons and making them jump up energy levels. And so that nebula is gonna stay there for the rest of, well, near future. At some point, of course, the gas is going to like slowly move out into space, and it might not be visible after some time. But again, that's way far in the future. And the white dwarf itself is just, it's not doing fusion or anything. It's just going to keep cooling and cooling off until hypothetically it becomes a black dwarf. The universe isn't old enough for it to exist any black dwarfs, astronomers posit at the moment, wherein it just emits no light or anything, just the core of the star.
So here we have it. Now, one thing about the cat's eye is it is a very small planetary nebula, relative to how we're viewing it here from Earth. So it's kind of this small bright circle in the center here, and we'll be able to get more detail out of it once we use other filters. So I don't know, Katya, would you like to try one with
Oh, I just tried the O3.
Perfect. That was
okay.
what I was going to suggest, actually. So yes.
And just read your mind.
So we're going to take one with another filter
Wonderful.
and try to pick out a little bit more detail. The cat's eye is probably one of the most studied planetary nebulas. There are some absolutely amazing Hubble images of this nebula specifically. And if you look around, I mean, you can find X-ray, ultraviolet, infrared, radio, any type of light that you can think of, you can find a corresponding exposure of this, as it's one that's been kind of thrown around a lot with those beautiful images. And when you kind of get those long exposures, there's quite an interesting structure that you can find in this nebula. Unfortunately, with the telescope with SEO, it's not quite as a kind of a smaller field as you would like, but this allows us to take images of other objects a lot better. And once we kind of get this O3 image back, hopefully be able to kind of pick out a little bit more in there. Now, you might be wondering, what kind of connection does this have to Yerkes? The connection for this one is not as straightforward as the other three, but it is an example of one of the stages of the life cycle of stars. And that is something that was studied for basically continuously throughout the entire existence of Yerkes Observatory. And Subramanian Chandrasekhar actually won the Nobel Prize in Physics for his research on the life cycle of stars. Kathy, do you want to tell us a little bit what the Chandrasekhar limit is? Because I believe that played a big portion into how he got his Nobel Prize.
Oh, right. Yeah. So yes, as Adam was saying, Chandra had a lot to do with stars and stellar evolution and the astrophysics and hydrodynamics, and he studied like everything ever imaginably possible related to stars. And so the Chandrasekhar limit of itself is basically if you have what I was talking about, a white dwarf star. There's a maximum mass that the white dwarf star can attain to be stable, and so above that mass, it's not stable anymore. And Chandra figured out that that mass is equal to 1.4 times the mass of our sun. And so usually with a white dwarf that has a mass greater than that, it will collapse under its own under its own gravity, basically, and it can become either a neutron star or even a black hole, depending on different physics and other properties of the star.
So discoveries like that, and a lot of his research went into some just absolutely mind-blowing discoveries, and he's definitely one of the most successful and well-renowned physicists to ever be at Yerkes Observatory.
Sometimes, like when visitors were at the observatory, we liked taking people to an office, and we were like, touch this doorknob, and they would touch it, and then we were like, this is the doorknob of the office that Chandra had at Yerkes.
See, the story I always think about when people kind of reference things like that at Yerkes is always in the men's restroom, one of the stalls that Einstein used.
Oh,
That's the story I heard
right.
quite frequently.
Oh, yeah.
But I like the
One
Chandrasekhar
is
one
like
as somebody who was actually there and really contributed to the legacy of Yerkes.
Yeah. Yeah, a lot of people think that Einstein like worked there or like did something, like did part of his research or something at Yerkes, but in reality he just came for a visit one day. It might have been multiple days. I don't actually know, but he never did any of his big like research relativity or anything at Yerkes. Okay.
All right. Well, I think, Katya, unless there's any other things that you would like to mention, we are just about out of time. I think we should start wrapping up right about now.
Yeah, so one other thing I can say is last time we received a request for a nice edge-on galaxy, NGC 4565. And last time we were unfortunately unable to get any good images because the seeing was not very good. But today and yesterday we had wonderful seeing and weather, And so we were able to take an image of it, and actually I was able to go and make a color image, and so I just want to share that for any that are curious and those that wanted to see it.
Yeah, and I think it came out really well, so I'm glad that you brought this up
Yeah.
before we went out. And if anybody wants some of these images, you just think they're cool, let me know and I can send you all of the images that we took today, or at least the good images that we took today, and just kind of send them in a little zip file. So you can just email me, my adam@glasseducation.org, go to our website, and kind of submit something there in the contact us portion. And don't forget that we do these every Friday night, so make sure you join us next week. And I'll actually let Katya talk a little bit about this galaxy first, since this is a cool one.
So this is, so you can see this is an image that I got basically by the same method as I did M51, just by stacking different filters together. And you can see the difference here is that before we were looking at the galaxy kind of on its like flat side. In this case, this galaxy is oriented so it's edge on, so we're looking right at the edge, so you can clearly see the nice dust lanes that go like diagonally across the image. This is also called, for the reason that it's on its edge, it's called the needle galaxy. It is also a spiral galaxy, actually, like 40 million-ish light years away. But it's hard to tell a little that it's spiral because you can't actually see the spiral structure in this case. Yeah.
Thank you very much, Katya. This is awesome, and we're actually going to keep the observing party going because we've got a couple hours left of observing time to use up, so we're really excited. But we want to thank all of you guys for joining us. If you enjoyed these videos, including the one earlier today, please go to our website, check out some of the stuff that we have going on there. And as always, since these programs are free, we do rely on donations, and all donations to GLAS are tax deductible, so get that in now while you can. But otherwise, thank you guys all for joining us, and we hope you have a wonderful night, and hopefully we'll see you guys next Friday.
Good night. Clear skies.